If you move fast, you actually age slower. To see that effect, you need to run at speeds comparable to speed of light, which is 3 million km per second. We usually think that running fast makes us lose our mass, but physics says opposite. Running fast gains us more mass. But chill, that also happens when you run at speeds comparable to speed of light. So that was what Albert Einstein wanted to say in his special theory of relativity. Albert Einstein gave two theories. Interestingly, both tells about slowing of time. Special theory of relativity, general theory of relativity. Special theory of relativity tells how time gets affected due to speed, and general theory of relativity tells how time gets affected due to gravity. In this video, we will be talking about special theory of relativity. For almost 200 to 300 years, physics was ruled by Isaac Newton. His laws explained how apple falls, how planets move, and how entire mechanical universe works. His laws worked so well that physicists didn't just believe them, they were the absolute truth to them. They treated his laws divine. Newton said that time was absolute. 1 second for me, 1 second for you, and 1 second for entire universe flowed at same rate. According to Newton, every object in this universe has to follow these laws that he gave. And for a long time they did. But one object or one thing that refused to follow his laws was light. Okay, how did physicists know that light wasn't behaving normally? So to understand this, we assume two balls, ball A and ball B. In first case, we assume that ball A and ball B are moving in same direction with same velocity. So if ball B looks at ball A, what will it feel? It will feel that ball A is at rest. But we know that these two balls are moving. So let's assume second case, when ball A is moving with a little bit greater velocity than ball B. So now what ball B will think? Ball B will think that it is at rest and A is moving slowly away from it. So let's assume third case. When these two balls, ball A is moving downwards and ball B is moving upward. When ball B looks at ball B will think that ball A is moving with very fast velocity. So this is the relative velocity concept and everyone is familiar to it in their day-to-day life. But let's ask an interesting question. What if ball A is not an object but it is light itself? Let's assume now that ball A is not an object, it is light. And we are sitting at ball B. So according to us, will velocity of light change? So physicists asked this question and everyone was confused that will speed of light change if we look it from a relative frame or a moving frame. So we all know that sound needs a medium to travel, and during that time physicists also believed that light also traveled in a medium. They called it omniferous ether, or we will say it's ether. So to figure it out that speed of light is changing or not, they did an experiment. It was known as Michelson-Morley experiment. So this was a setup: a light beam source, beam splitter, mirror 1, mirror 2 and a detector. So they assumed that if light is flowing against the flow of ether, its speed will decrease, and if it is flowing with ether in direction of flow of ether, then its speed will increase automatically. So to figure that out, they did this setup. First time, when the beam was released and the splitter splitted that beam into two perpendicular rays, and those perpendicular rays converged and were reflected towards detector, they saw a fringe pattern. So first time the light was with the flow of ether, and second time when they rotated the whole setup 90 degrees and they again released a beam, they believed that fringe pattern on pattern will change a little bit, and this will prove that ether was there. A medium through which light travel will be proved. But what they saw that pattern wasn't changed. It remained the same. So rather than proving ether, this experiment disproved ether. So this proved that there was nothing called as omniferous ether in this universe. So this experiment was repeated in many parts of world at many different times, but the result was same. This experiment showed that speed of light is always constant. No matter what, no matter where you are, no matter how fast you are going, it will always remain constant. It will always remain same. Speed of light will not increase or speed of light will not decrease, no matter what. So this leads to a conclusion. What conclusion? The conclusion that time is not absolute. It flows differently for everyone. 1 second for me might not be same as 1 second for you or 1 second for everyone. How this proves that if speed of light is constant, then time is not absolute for all. We know that formula speed equals distance upon time. This is the very first thing that we study in physics. To calculate speed, you just divide distance by time. So what if we substitute c in space of speed? So to understand this, we will also consider two cases. In case 1, we assume there are two parallel mirrors facing towards each other and a clock which is also ticking by side. They are placed at a distance d from each other and a beam of light is released from lower mirror. So when it is released, clock will tick. When it touches the above mirror, clock will tick again. When it comes back and touches the lower mirror, the clock will tick again. So seeing this case, if we substitute all the values in speed formula, c equals distance upon time, where d is small d and time is t. Case 1 was that this system is at rest. In case 2, if we assume that this system is moving with velocity v, when light is released from lower mirror and it touches the above mirror and comes back to lower mirror, we will see that light has traced a diagonal path. This distance we will represent as capital D. So this distance, which is denoted by capital D, is obviously greater than small d in previous case. Now that formula c equals distance upon time, if we substitute c equals capital D upon t, we can compare these two formulas. In first case, right hand side is same, left side has changed a little bit. In case 1, the numerator is small and in case 2, numerator is very big. So we have to keep our right hand side same, which is speed of light. Speed of light cannot change. So to keep speed of light constant, what needs to be changed here? That's obvious. We have to change time. So time is changing. So this conclusion that speed of light is always constant also concludes that time is not same for everyone. Time is different. Now if time is not same for everyone, then Galilean transformation equation failed, as they are based upon the very thing that time is always constant. Time flows at same rate for all universe. So this is proved if a body is in motion, time will change for it. But Galilean transformation equations failed. So new kinds of equations were needed to understand this time dilation. These equations were called Lorentz transformation equations. So Lorentz transformation equations has a lengthy derivation, which if you want you can do, but we don't need its whole derivation. What we need is the conclusion, the equations that make this concept of time dilation understandable.